In the coming period, we'll take examples of nucleophilic addition reactions. We begin with hydration. So hydration is the first nucleophilic addition reaction that we will talk about now. So hydration. And as the name suggests, hydration is a reaction with water. Formaldehyde undergoes equilibrium reaction to form the corresponding addition product, the corresponding hydration product, where there are two hydroxyl groups attached to carbon of the carbonyl group. That's a diol. So let's write that reaction. Formaldehyde undergoes equilibrium with the corresponding hydration product. If you look at that product, it's actually a diol. This is called a 1,1 diol or a geminal diol. So this is geminal diol or gem diol. Where there are two hydroxyl groups attached to the same carbon. Now this hydration reaction is very important in this case of formaldehyde. It is, however, less important in general aldehydes and much less important in the case of ketones, and that's due to sterical hindrance, sterical bulk around the carbonyl group. Now, this hydration reaction can be actually catalyzed by an acid or a base. So if we take formaldehyde, a base such as the hydroxide ion, for example, can attack. So that's the hydroxide ion, which can come and attack, and it attacks carbon of formaldehyde, and this carbon oxygen double bond simultaneously breaks. If that happens, we get something like that as a product. So that's the hydroxyl group which has attacked in the nucleophilic addition reaction. This intermediate alkoxide gets protonated in a subsequent step. So this is that's water basically. So we can protonate this alkoxide by water. So the alkoxide or the negatively charged oxygen picks up a proton from water. This hydrogen-oxygen bond therefore breaks, and this gives the product with regeneration of the hydroxide ion. Because it is a base catalyst, it is regenerated, recycled, which can be further used or reused to react with another mole or another molecule of formaldehyde. So this is base catalyzed hydration. Hydration reactions can also be catalyzed by an acid. So let's see what happens if we take formaldehyde, but this time we react it with an acid catalyst. So this is like the hydronium ion, for example. So that's the hydronium ion. Now we've seen before that oxygen is actually nucleophilic. It's also Lewis basic. It's basic. It can get protonated therefore by reaction with a proton source or with an acid. So something like that. Now we get this intermediate protonated formaldehyde. Now this protonated formaldehyde is actually more electrophilic at carbon of the carbonyl group because of that positive charge on oxygen. Now what happens is that now water will come and attacks that electrophilic carbon like that. So this is again a nucleophilic addition on the more electrophilic carbon of the protonated aldehyde. If we do that, we get something like this. The last step will be for a water molecule to pick up one of these hydrogens on that from that positively charged oxygen, giving rise to the product with regeneration of the acid catalyst. So a water molecule now will come, and water will pick up that proton, and at the same time this hydrogen oxygen bond breaks, giving electrons of that bond to the positively charged oxygen. Now this gives the diol product plus the hydronium ion regenerated as a catalyst. And it should be regenerated because it is a catalyst, a species that speeds up the reaction but never gets consumed. So in this hydration reaction, the reaction can either be catalyzed by a base, so this is a base, or by an acid such as the hydronium ion. So acid or base catalysis allows hydration reactions of aldehydes and ketones in general to form the corresponding geminal diols or 1,1 diols.